This is lesson 18, the rate expression. So at any particular point in a reaction, if you're keeping track of the concentration versus time of either the reactants or products, you can find the rate at a certain time by taking the slope of a line tangent to the curve at that time. If we want to know the instantaneous rate at the beginning, or the initial rate, you would just take the instantaneous rate, so the slope of a line that you draw tangent to the curve at time 0. AP often asks for the relative rates of reaction. So here's an example. If 2 moles of hydrogen iodide are disappearing for every 1 mole of hydrogen gas you're making and 1 mole of iodine gas that you're making, we know that the rate will be equal to minus, because these are going away, 1/2, because the coefficient is 2, concentration of HI versus time, or the rate will be equal to the concentration of H2 over time, or the rate will be equal to the concentration of I2 over time. So in general, if your reaction looks like this, where the little letters are the coefficients and the big letters are your reactants and products, the rate is going to be equal to negative 1 over little a, because that's the coefficient here, just like 2 was in this reaction. The concentration of A over time equals, which is equal to the negative 1 over B, which is the coefficient here, of the concentration of B over time. And then since you're forming products, the rate would also be equal to 1 over the concentration of, or 1 over the coefficient C times the concentration of C over time, which is also equal to 1 over the coefficient D times the concentration of D over time. The rate expression shows the relationship between the reaction rate and the concentration in a chemical reaction. So we talked last lesson about how if you increase the concentration of reactants, you're going to speed up your reaction. So the rate only depends on the reactants. So here we have A plus B going to products. And we know that if we increase either of these concentrations, we're going to speed up the rate. So the rate is equal to a constant K times the concentration of A to some power times the concentration of B to some power. So M and N are always the orders of the reaction, and if you add them together, you'll get an overall order for the reaction. And K is the rate constant, which changes with temperature, but otherwise remains the same. So here's an example. The reaction 2 hydrogen plus 2 nitrogen monoxide goes to 2 water plus nitrogen gas is shown to be second order with respect to NO and first order with respect to H2. Give the rate equation for this reaction and its overall order. So rate is equal to the constant K times the concentration of H2, and they said it was first order with respect to H2, so there's no exponent, times the concentration of NO, which they said was second order, so we put an exponent of 2. So its overall order is 1 plus 2, which is equal to 3. So it's third order. So what's important about this reaction to realize is that the order of a reaction does not equal the coefficients in the balanced equation. The coefficients cannot tell you anything about the rate. The rate can only be determined experimentally. Now, the units for K can change. They're dependent upon the order of reaction. And to find the units, you have to use the rate expression. And we'll do lots of these examples in class. But K can tell you how fast a reaction will go. So if K is very large, you're going to have a fast reaction. But if K is very small, you're going to have a very slow reaction. Now, a zero order reaction, when the exponents all add up to 0, means that really the concentration is not included, because anything to the 0 power is just 1. So the rate does not depend on the concentration of the reactants. So you can add as many reactants as you want, the rate will not change. In a first order reaction, meaning that the exponents add up to 1, the rate is going to be directly proportional to the concentration of that reactant. And in a second order reaction, the rate is proportional to the square of the concentration of the reactant. So here we have 2 for our overall order, and the rate will be proportional to the concentration of A squared. So how do we determine the order of a reaction? Well, a series of reactions must be done to determine the rate expression, which is called the initial rates method. If you change the concentration of A and there's no effect on the reaction rate, it must be zero order. But if you change the concentration of A and the rate is proportionally changed, it must be first order in A. So for example, if you double A and the rate doubles, it must be first order in A. If you change the concentration of A and the rate changes by the square of the change, the reaction must be second order with A. So for example, if you double A and the rate increases by 4, it must be second order in A. So here's an example. Use the data in the table below to work out the order of the reaction with respect to reactants A and B, and then write the rate expression. So here there's 5 experiments, and there's 2 reactants A and B, and here they've changed them. So the same concentration, and then they double A, and then they triple A, and then going from here to here, they keep A the same, but they double B, and going from here to here, they keep A the same, but between 3 and 5, they triple B. So here they give you the rates to all of these experiments. So how are you going to do this equation, or do this problem? The easiest way to do these is mathematically. So we know that if we compare, or if we write the rate expression for this, we're going to have some constant K times the concentration of A to some power times the concentration of B to some power, M and N. And we know that if we compare experiment 2 to experiment 1, where A is doubled but B is the same, we know the rates. So the rate of 2 is 4 times 10 to the negative 4th, and the rate of 1 is 2 times 10 to the negative 2nd. So if we plug those in, we know that the rate of experiment 2 is some constant K times concentration of A, 0.2 to the M, times the concentration of B, 0.1 to the N. And we know that experiment 2, the rate is equal to K times 0.1 to the M times 0.1 to the N. And just looking at this, we can see that these are going to cancel because they're the same, and K's are going to cancel. So if we divide this, we get 2, and if we divide 0.2 by 0.1, we get 2, and then we have the M power, so we can see that M has to equal 1. Well, now we can do the same thing to find N. So for N, we need an experiment where A stays the same, so 4 and 3, but B changes. So here, 4 and 3, B is changing. So again, the rate of 4 is going to be equal to K times 0.3 to the M times 0.2 to the N. And for 3, it's going to be 0.3 to the N, M, times 0.1 to the N. And then we can plug in our actual rates, 2.4 times 10 to the negative 3rd, and 6 times 10 to the negative 4th. And we will get, canceling out our K's, canceling out our 0.3 to the M's, 2 to the N is equal to 4. So we can see here that N must equal 2. So our rate is going to be equal to rate times K, rate equals K times the concentration of A to the M, which was 1, times the concentration of B to the N, which was 2.